Hi, welcome back. This is the part two of videos. We will going to discuss about the lung volume and compliance. So we should start. Okay, so we in this part we will talking about the lung volumes and what is about the lung compliance. So here are a graph of different lung volumes. We can see it in here. In here, in this part of section, the person is told to just, breathing normally. And it shows this is what we call a tidal volume. That the volume is approximately a half a liter. Okay. Um, at this point, just normal breathing, normal breathe in and normal breathe out. But if you told to inhale as much as you can, and then we call it the inspiratory reserve volume. That's what's shown right here. Is this the portion of the curve? So the most of these values can be measured with just a handheld spirometer. It's very easy to measure these values. These values are going to be important for the disease. So these values can also change with the disease. So this is, we call it the inspiratory reserve volume. And then you can do a normal exhalation and then you can exhale as much as you can. So we call it is expiratory reserve volume. So the inspiratory reserve volume is about 2,500 ml and the expiratory reserve volume is about 1,500 ml. So this is what we call the inspirational capacity, which is the inspiratory reserve volume plus the tidal volume. So the inspirational capacity is about 3 liters. And we can call it the vital capacity if we can just add inspiratory reserve volume plus tidal volume and plus expiratory reserve volume. So we call it a vital capacity, or vital capacity is inspirational capacity plus ERV, right? It's approximately about the 4,500 milliliters. So we also have that we call residual volume. Okay, so there is when you exhale completely, you still have air in your lung. Otherwise, your lung will completely collapse, so which is very difficult to overcome because the surface tension of the water. So this air is left in the lung, a perfectly normal and very, very important. We call it residual volume. It is approximately 1,500 mils. We can put these numbers together and come up with the capacity. So we call it the functional residual capacity is the ERV plus residual volume. Okay, so we can just add all into the total lung capacity. It's just the vital capacity plus residual volume, or the inspirational capacity plus the functional reduction volume. So this is the number that volume that we can measure except for the residual volume, right? So the residual volume cannot be measured by spirometry. Why? Because the spirometry is just want to measure or just able to measure the air that can in and out from our lungs. The residual volume is not in and out from our lung. So spirometry only can measure all of this except the residual volume. Okay, so in this part of this slide is just just break down all the definition about each volume and its capacity. Now we are going to switch to talking about the two lung disease. So in here, we are going to talk about the two types lung disease, the obstructive disease versus restrictive disease. So we'll be reviewing these two throughout the video, okay? As I mentioned before, that in obstructive disease means that the people is hard to expire, you know? So the problem with exhale. Okay, so um, that often means that the residual volume can increase because some of the air is just left out after the exhalation. Example of this would be in asthma, when you're going to have inflammation and contraction of the smooth muscle in the airways, so that you're going to have difficulty to bring the air out and increase resistance. Another example is COPD, the chronic obstructive pulmonary disease, which comes in two types usually. The first is chronic bronchitis, which is where you have a lot of mucus in the airways. The second one is emphysema, when they have alveoli that destroy. The problem is due to a lack of elastic tissue, which means that the lung is very easy to open and fill, but then it doesn't have the recoil to exhale. In some of this disease, you can also get collapse of the small airways. So I want to repeat it one more again. Obstructive disease means that the person is getting difficult to exhale or expire. Okay, it is because due to increased resistance in the airway, like in asthma or chronic bronchitis, but it can also be due to the destroy of the alveoli, like in the emphysema. Okay, so now we are going to talk about the restrictive disease. The restrictive lung disease is those which can the lung cannot expand for some reason. So total lung capacity is then decreased. One example of this is when we consider the fibrosis in tuberculosis, which is the connective tissue in the lung is added, which there is increasing connective tissue in lung. Connective tissue doesn't do stretch, right? So the elasticity of the lung has been removed. You can just stretch as much as the total lung capacity lung decrease. Or also you can see the condition called the scoliosis, when there is a deformity in the spine. So they can just expand the lung as normally they do. So it's going to have the same effect of preventing a large increase in volume and reducing total lung capacity. So obstructive is hard to expire. The restrictive is hard to inspire. Okay. So we're going to use this diagram to look what happened uh, about the lung compliance between the pressure and lung volume. Okay, which is the compliance is also we call the distensibility. Okay, this diagram have transpulmonary pressure in the x-axis and the lung volume in the y-axis. Okay, you can see that when you change the pressure across the lung, you can see also the changes in the volume. Okay, you could think of it is as if you apply a certain amount of force basically to open the lung, how much does it open and how much does the volume increase. That's what we shown here. If you apply a certain pressure, okay, the lung will open and then continue in the pretty linear fashion to increase the volume until you get up here when you're starting to get the plateau. And that makes any sense because they're already full, that you cannot expand more. You can apply a lot of pressure, but you cannot getting bigger because it's full. So it's perfectly normal. It makes sense. This is kind of a normal amount of compliance, which you can also think as distensibility. So compliance is how easily is it open. Now the thing to keep in mind with the lung is as compliance increase, the recoil is going to be inversely proportional. So if compliance increase recoil, which is the amount that is going to shrink, is going to be changed in the opposite direction. So compliance is how much you can open, how easily it can open, but the recoil, how easy it can shrink again. And they're, proportional inversely. So if compliance increase, the recoil will decrease and some vice versa. Okay, in the normal lung, you get kind of an immediate medium amount of compliance and medium amount of recoil. But you have a disease when you have increased compliance like emphysema, right? It is very, very easy to open the lung. There's nothing problem with opening the lung. You can see we're applying a small amount of pressure and we're getting this huge lung volume increase, right? They have increased compliance. But if you have increased compliance, that means recoil has gone down. You can think of this as in emphysema, the elastic tissue has been destroyed. That means you've got nothing to oppose opening the lung. So it means it's easy to fill in. But then the problem is you need the elastic tissue to recoil, right? To get shrink again. But in the emphysema, due to the destroy of elastic tissue, you don't have any elastic component of the lung, so it will be less recoil. So you made it easier to breathe in but harder to exhale because you increase the compliance and decrease the recoil. To make it easier, so just take another example of the extreme, right? You can just take a paper bag, when you're just going to throw out in the air freight or something like that, and you just blow into the air paper bag. The air paper bag is just easily get filled in, right? But the paper bag doesn't have any rubber or something like that, the paper bag doesn't have ability to shrink again. So there's no problem to fill in the air in the paper bag, but there's no capability to get the air out. So that's what we call it, high compliance, no recoil. All right. And this happened to like just a disease called the emphysema. Okay, let's talk about the other situation when we have decreased compliance, which means we're applying a lot of pressure, right? And the lung volume is not increasing very much like in the normal situation. All right. So we got, let's say, an increase in connective tissue like in the fibrosis. This means that lung just aren't going to stretch the way they should. It will take more force, energy, pressure to get air into the lung. So we decrease compliance, but that means that we've increased recoil. It's going to be easy to get the air out, but very hard to get the air in. So example, when high compliance is just a paper bag, decreased compliance, just like we blow out the balloon, right? We have to push some effort to just fill in the air within the balloon. But we just stop the pressure, the air in the balloon will just come out very easily. It's just an example of no compliance, high recoil. Can you understand about that? Okay. Okay, we're going to go in the next slide. So what is important about the lung compliance? What is the factor that influence about the lung compliance? We already talked a little bit about the elastic tissue, which will make it harder to fill it, but definitely will provide the recoil of the lung. In emphysema, we're destroying the elastic tissue and so compliance increase. In fibrosis, we're adding connective tissue that doesn't stretch the lung, and so the lungs are not as distensible. Compliance is going to decrease. Okay. The other factor is also influence the compliance is the lung surfactant. Remember, the type 2 cells of the alveoli make surfactant, right? They actually make it response to the lung being stretched. Surfactant is a detergent-like molecule. That's what's shown down here. It has a hydrophilic and hydrophobic portion of the molecule. That is what helps it reduce the surface tension of the water. Every time we breathe, we can expand the lung. We have to fight or to combat the surface tension of water. We have to overcome that force. The surfactant reduces the surface tension so that it doesn't require as much force to open the lung. This is most easily demonstrated in the certain premature babies who, because they premature, are not yet making surfactant. To breathe, just normal breathing requires a tremendous amount of energy for this baby. They can die from exhaustion trying to breathe. It's very illustrative example of how much force it takes if you don't have surfactant in your lung. Another issue in the surface tension situation is that our alveoli in our lungs aren't going to be the exactly same of size. If you remember about the law of Laplace, say that the pressure will be um, because since a radius, a radius involved in the pressure in the alveoli. So when we have this different size of radius of alveoli, the pressure also will be different. And then the air from the smaller diameter of the alveoli come will just come into the larger alveoli. This is not what we want. Okay, so when we have surfactant, and then this amazing thing about the surfactant is the surfactant, I don't know how, have preferentially choose smaller radius of alveoli. So the smaller radius of alveoli will have more surfactant than this large radius of alveoli. So that now that small alveoli and the large alveoli have the same pressure because the smaller alveoli have increased the surfactant, the surface tension. That's what's shown here. It lowers the surface tension in the smaller alveoli more, so that even though they have a different radius, the pressure in alveoli number 1 and 2 are the same. So that's another important aspect of surfactant, just based on its molecular properties that is able to do that. Okay, so I want to repeat again once more. Okay, you want to be, you want to have this pressure equal in these two different sides of alveoli, right? The law of Laplace say that the pressure in the alveoli is going to be equal to 2 times the surface tension divided by the radius. So if you have a smaller radius, you have the bigger surface tension. So you will have the same pressure. Okay, we've talked about the different lung volumes, how we can measure them, and how they can, Another issue in the surface tension situation is that our alveoli in our lungs aren't going to be exactly the same. Because of that, then you have to worry about what's happening in the pressure. Okay, so we come to the last slide about the key concept. We talk about different lung volumes, how can we measure them, how they can change a little bit in the disease. We'll be talking about that more in the future. Then we also talk about the compliance. The compliance is the measurement of distensibility. The compliance will increase when the recoil will decrease. They are inversely proportional to one another. And we'll talk about how in restrictive lung disease, the lung is going to have low compliance but have high recoil. In an obstructive lung disease, we will have high compliance but low recoil. And we'll be talking more about these two types of disease in the future session. Thank you. We will have you in the part 3. See you there.